then you introduce the icon. Okay.
Sure, sounds good. Yeah, we're recording.
Okay, so let's start our distinguished seminar. So first, welcome everybody. So please sit in front if you could. And this is perhaps our the end of semester event. And first, good afternoon and welcome to Icon events, distinguished Icon seminar. And today we have a very special speaker, and we will have actually our assistant dean to introduce the speaker. But before that, I want to invite our co-director for Icon, now is Institute for Control Optimization Networks, Shreya Sandran, to introduce Icon. Yeah.
Hey everyone. Hey Brian. Sorry I can't be there in person. I'm in Albuquerque, but thanks so much for coming back to give our second. You're the second distinguished seminar speaker that we've had at ICON, which is now an Institute for Control Optimization and Networks, as Shashway indicated, and this is sort of our kind of our official announcement of that fact. So Brian, it's a great pleasure to have you. He gave the Distinguished ICON seminar in February 2021, one of our first distinguished speakers. Since that time, ICON has grown to almost 80 faculty now, and are continuing to expand and tackle big problems. And so it's a great pleasure to have you here and see the new research that you're going to be talking about. So I'll turn it over back to Shashway.
Yeah, thank you, Shreya. This center is more like now it's the Institute of College Collaboration, and actually we got a great support from our college, and especially our associate dean Wen Chen. So I would like to invite Wen Chen to say a few words to welcome our speaker, and also say a few words. Thank you. Please.
Thank you. I hope I'm loud enough. I actually teach in this classroom. So the best place is actually in the middle somewhere. You sit top there actually without very much. So welcome to this distinguished seminar. At Purdue University, Special Engineering. I think that all of you know that we are big. So the advantage of being big is to form something like the Institute of ICON, that all of a sudden we have 80 faculty members that participating. You don't see this kind of scale anywhere actually in the country. So we have lots of energy. We have young leaders with a very energetic attitudes serving all the institutes serving the people. In the meanwhile, we need very high level intellectual interactions. So we have world-class leaders in the field, like Brian Anderson here, to show us what needs to be done and how we do things in a rigorous way, which are the directions that you go, combined with the energy and the scale we have. And I'm confident that ICON is going to be very soon will be the world leading institute in this field. Yeah, so congratulations for the achievements so far. I look forward to Saturday. And actually, I'm introduce that assistant dean, George Chu, who's an expert in control, to introduce our distinguished speaker.
Thank you, Wayne. Thank you.
Thank you very much, Wayne. We kind of made it unnecessarily complicated handshake to test our robustness of the process. So my name is George Chu. I'm a professor of mechanical engineering, and I'm also the assistant dean for global engineering programs and partnerships. It is my great pleasure to introduce our speaker today. And everybody knows, I really don't need to introduce Professor Brian Anderson. Professor Anderson is a professor emeritus at the Australian National University, where he held the distinguished professor there for many, many years. And Brian has won pretty much all the awards that the community has, including the IEEE Control Systems Award, the Plaza Medals, and the Mulligan Education Award, and he also served as the president for the International Federation of Automatic Control, IFAC. Brian is also a member of many academies in many countries. He is the members of, and also the chair of the Australian National Academy of Science, as well as the National Academy of Science and Technology. He's also a member of the Royal Society, and he's also an international member of the U.S. Academic Academy of National Academy of Engineering. And he's going to speak to us today about a very interesting topic, which it's a no minefield when you go and interview, talking about Extrema without complexity and stability without Lyapunov. Sounds very, very interesting. So let's give a great welcome to Professor Andrew. Thank you.
Oh, yes. I also saw some online students, including Zhiyong.
Yeah.
Is also here. And also, we have also some faculty like auto here.
Management.
Just, can you see the slide?
That's perfect.
Yes, we can.
I hope everybody can hear. Let me begin by thanking the people who introduced me, George and Wayne. And of course, it is a pleasure to be here. And I think on my next slide, I have a more formal thanks to Xiao Shui. Shreya, I should also thank you, and I'm sorry you're not here this week, but I know we're meeting on by Zoom on Friday. I did meet Xiao Shui Mo about 14 years ago, when he was, I guess, a new graduate student.
Yeah, new PhD.
Yale University. And I guess we clicked. And I did count, I don't know, a month or so ago, when I was comparing these slides, 29 words, which is a pretty fair number, isn't it? With him and his students since that time, all done with, you know him for being very enthusiastic. Well, I'm very enthusiastic working with him. And I do want to thank you, Xiao Shui, for hosting me again. I should probably have written one of the leading icon centers in the world, but I'm not sure that the center's been long enough in existence to have the fame that the school has had now for many years. So to get on to the object of the seminar, you could say I'm almost preaching. I want to convince you of the danger of signing up to a single ideology. It seems to me almost any time you hear the word optimization, there's a high probability you'll hear the word convex or convexity or some other grammatical form with the same root. And I want to suggest to you that there are sometimes other ways of doing things. And those other ways of doing things here we go. So Xiao Shui, can you show me this thing's not done? Okay, well, we seem to be working now. Thank you. Sorry about that. So I'm going to tell you about a little known theory that had its roots in the 1930s, but has had many developments since, including in the last few years, and finds great application today in the power systems area, but I'm not going to be talking about power systems. I do want to demonstrate how useful this theory is with some examples that I myself have been involved in. It's called Morse theory, and here are some references on Morse theory. And if you've never read it before, you probably should read reference 1. And then probably reference 3 or reference 4, and the last one you would read because it's the most complicated is reference 2. So the application areas that I know most about are in localization, target localization, controller design, robot motion, and formation control. And what I'm going to do is talk about Morse theory as a package. I think there's maybe 10 or 11 slides on that. And then explain how you can do minimization
without having a convex function that you're optimizing. And then I want to talk about the 4 applications. If there is time, I'll talk about the most recent developments in Morse theory, which are called Morse-Smale systems, but there might be time. So convexity is a crucial tool in optimization. But convexity is not invariant to bijective transformations. What do I mean by the detail of that statement? Well, if you look at that graph on the right-hand side, it's the graph of f of x equals log of x squared plus 4. And it's obviously got a minimum, and it's obviously not convex. But if I worked, instead of working with y, f of x, if I worked with the exponential of f of x, I would have something that's convex. And what I'm telling you is that if you make a bijective transformation, that is, if say you move from r theta coordinates to xy coordinates, or r theta phi coordinates to xyz coordinates, you may lose convexity. And what was a nice problem to solve because of convexity of the loss function, the cost function, is no longer convex because you happen to have chosen the wrong coordinate basis. Bijective transformations are what allows you to change coordinate bases. So there's a danger in looking for convexity as your main tool, because that's requiring you to get the right coordinate basis to describe the problem. Convexity is not invariant to bijective transformations. But here's a point, and it's this box down at the bottom right. At the critical point, that is at the minimum, even with the bijective transformation, convexity is preserved. It's just the whole curve is not necessarily convex if you start with a convex curve and then bijectively transform it. But if the critical point itself is locally convex, bijective transformation doesn't destroy convexity right at the critical point. So because topology, differential topology particularly, is mainly concerned with concepts which remain invariant given bijective transformations, convexity is not really a topological concept. And Morse theory is, as you will see, a topological concept. And I want to assert to you that there are topological concepts which are useful in optimization and control. And that's what my 4 examples are all about. And they're topological concepts because they are invariant under bijections, and convexity isn't. These topological concepts, of course, there's enormous variety of topological concepts, but the 2 big ideas that are relevant to control and optimization are these. The first is that you can often get global information simply from local information, especially local information concerned with the critical points of the function. And again, this will be illustrated with my examples. So we do have to make some assumptions in advance. That's inevitable in any theoretical work, I guess. And the typical examples here are that you've got smoothness, and perhaps for very large values of the argument, you go off to infinity or something like that. The second idea where topology is important is that the local nature of the critical points, whether you've got minima or maxima, so on, can often be studied using some funny equalities and inequalities, and these are the things actually due to Morse. So I'll be showing you what those are and how they can tell you about the behavior of the critical points. So the 2 ideas are that from local information, you can sometimes infer global information, and by using Morse's equalities and inequalities, you can learn about the nature of critical points. And these are the most technical words in the seminar, I guess, Euler characteristic and Betti numbers, and I'm not even going to define them, but these are numbers associated with spaces. They're topological numbers. Euler, you'll appreciate, was several centuries ago, and Betti, I think, was 19th century. So these are not recent developments of the last decade or anything like that. It's just they're not in the standard lexicon of control engineers. I'm not even going to define them, but I want to assert that they exist and ask you to accept that and tell you that if you want to know the Betti numbers or the Euler characteristic of a circle, you can look it up somewhere. And it's just a number, an integer number, maybe with a negative sign. Boy, this thing is. What it is?
I think
It is something magic.
no, I'm not sure. Maybe the country. Sometimes it's not. Maybe you can use the trick. Maybe it's good.
Yeah.
It may interrupt by
Someone's interrupted
in the Zoom. I believe.
in Zoom.
Oh, no.
Okay, so
No,
I
it's
almost have to sit here. Okay. So exploiting these things may make optimization easy. Okay. So what does Morse theory actually say? So here's a picture of a Morse function, and a very simple looking function. And you'll see it's bounded below, and it goes to infinity for large values of the argument. It's smooth, and the extrema are isolated, and the second derivatives are non-zero at the extrema. At the minima, the second derivative is positive, and at the maxima, the second derivative is negative. And the property about the second derivatives is invariant to bijection. And here are the observations I want to make about this function. First, obviously, it's got 3 minima and 2 maxima. And in fact, the number of minima you see is the number of maxima plus 1, because 3 is 2 plus 1. But if I had any Morse function, f of x, where x is a real variable and f of x is a real variable, then it remains true that the number of minima is 1 more than the number of maxima. Of course, the thing's got to go to infinity. When x goes to plus infinity or minus infinity, it's got to be smooth. You need the minima to be isolated and so on. And if that's true, the number of minima is the number of maxima plus 1. And if I got a secret message saying that I've got a Morse function here and I found that all the extrema are minima, you could immediately conclude that there was a unique, there had to be a unique minimum. Because if all the extrema are minima, there's no maximum. All the extrema are minima, if there's no maximum, number of minima is the number of maxima plus 1, so the number of minima is 1. So if all the extrema are minima, we have a unique minimum. And we haven't used convexity for that conclusion. And that's a conclusion that's very, very evident just for a scalar function of a scalar variable. So you could do this on a circle. That is, you could, instead of x running along the real line, x could run around the boundary of a circle, will be theta, and so it repeats itself with 2 pi. And so there's a picture where x has got, giving you the periodicity as it runs around the circle. And so it's like a periodic function on a line, in other words. It's bounded, it's smooth, the extrema are isolated, and the second derivatives are non-zero at the extrema. And the observations here are that we have 3 minima and 3 maxima, and the number of minima equals the number of maxima, and that happens to be true for any Morse function on a circle. The number of minima equals the number of maxima. And you can get from the line to the circle by taking black line and adding a red bit over the top and inventing some value for the function around the red bit, and then it's like what's going on in the circle. So those two rules, one for the line and the other for the circle, it can be obtained the one from the other with this sort of thinking, and I won't bother you with the details. So what happens in 2 dimensions? So here's a map. Might be a map of Indiana, except I don't think there's any mountains, are there? Anyway, in 2 dimensions, a Morse function is still bounded below. It goes to infinity for a large X. It's smooth. The extrema are isolated, and the second derivatives are non-zero or non-singular at the extrema. So these are the same conditions really as before. So actually you could be looking at part of the map of the Earth, which is a sphere rather than a plane. So now in 2 dimensions you have maxima and minima as before, but obviously you've got saddle points. If you've ever done any hiking, you'll know there's such a thing as a saddle, and that's an extreme point at which the Hessian has one positive and one negative eigenvalue. So we can ask, what's the analog of saying the number of maxima is one less than the number of minima, or the number of maxima is the same as the number of minima? But we have to take into account we've now got maximum, minima, and saddles. So we can call MI the number of extrema or critical points where the Hessian has I negative eigenvalues. I don't know who this person is. Okay, now it's working.
Yeah,
Is that okay on there?
Yeah, sometimes
I'm sorry, it's just jamming.
sometimes they're interrupted by Zoom.
Yeah. So M0 is the number of minima, M1 the number of saddles, and M2 the number of maxima. And this is what the Morse thing looks like in 2 dimensions. There's at least one minimum, that's an inequality, M0 greater than or equal to 1. There's always this inequality between the number of saddle points and the number of minima. The saddle points couldn't be 2 less than the number of minima. And there's a single equality that relates to the number of minima, maxima, and saddle points. And that's the story for Morse functions in 2 dimensions. And if you were asking about Morse functions on the surface of the sphere, like the Earth, what happens is the first 2 inequalities hold, but the last one's replaced by an equality. So this moves from 1 dimension to 2 dimensions. And for Rn, the same sorts of rules about F being smooth and isolated critical points and going to infinity. And now there's a possibility of different kinds of saddle points. And we get this generalization of the 1-dimensional and the 2-dimensional result, which is shown here, a whole bunch of inequalities and an equality. So this is all done in the 1930s. And it also works for a hyperrectangle if F has its minimum inside and is pointing outwards at the walls of the hyperrectangle. So just before I go on to some applications, I want to mention that it doesn't just have to work for Rn, or for that matter, an n-dimensional sphere. There's a set of inequalities and an equality for an arbitrary n-dimensional manifold. And this might include all orthogonal matrices, all 3x3 orthogonal matrices. That's a manifold. So again, the usual rules about F having to be smooth and isolated critical points, and MI is such that M0 is the number of minima, Mn is the number of maxima, and Mi is a particular sort of saddle point. And associated with an arbitrary manifold, you look up in your dictionary of Betti numbers and Euler characteristics, what the Betti numbers and Euler characteristics are of the manifold with which you're working. So Rn, Sn, orthogonal matrices, and so on. And here there's the Morse inequalities and the Morse equality. And the left-hand side is the same. And on the right-hand side, you have to put in these integer numbers, Betti numbers, and the Euler characteristic, which are peculiar to the particular manifold. And that's really all you know, all you need to know, and I'll be revising it in the next few slides about Morse theory in order to understand the applications that I now want to talk about. So the first is what I call minimization without convexity. And this underpins some of the applications. Morse theory gives us conditions under which we've got a unique minimum, and I indicated what these were for a one-dimensional function. But suppose we've got now a function of Rn, and somehow we're able to show that every critical point is a minimum. Then there's a unique minimum, and that's an immediate consequence of the Morse equation. Because if every critical point is a minimum, Mn minus 1 down to M1, they're all 0. The only critical points we've got are minima, and therefore they're sitting in M0. So the left-hand side of this equation is just minus 1 to the M0, where M0 is the number of critical points. But if that's minus 1 to the n, clearly M0 is 1. So the theorem is, if is acting on Rn to produce a real number, and every critical point is a minimum, then there's a unique minimum. You don't need convexity to draw the conclusion about the unique minimum. M0 again is the number of minima, and Mi, the Mi are all 0 in this situation. So you could say what's happening here is that a global result is following from local properties and counting. The local properties are the fact that every critical point is a minimum, and counting is really the counting result of Morse, which says a certain equality has to relate the numbers of critical points with certain characteristics, and from that we get that there's a unique minimum. Okay. And that minimum then can always be found by a gradient descent algorithm. Again, whether or not f is convex. If there is a minimum, f will be convex at the minimum, but it doesn't have to be convex away from the minimum. And that allows you to do a gradient descent on many manifolds that arise in systems work. So let me give you the first application, which is to nuclear source detection. So the idea is here we've got a nuclear source that's at some unknown position, x0, y0, and we'd like to know where that nuclear source is. And we have a detector that's moving along a street. The name of the street is x-axis, and the detector is picking up clicks that are arising in its counter from the radiation emanating from the nuclear source. And the detector, to keep it simple, is moving at a constant speed v, and the source is radiating alpha particles or whatever it is, and it produces a random process at the detector, which is an inhomogeneous Poisson process, to be quite technical about it. And because it's inhomogeneous, the arrival rate, the mean arrival rate, varies with position. And if you assume a mean square law, which is reasonable, This is the mean arrival rate of particles at the detector when it's time t, and so the detector's at the point VT along the axis. But we don't know A0, we don't know X0, and we don't know Y0. We just get a whole series of clicks at different times t. So we'll call these arrival times T1 through Tn. And the aim is to take T1 through Tn and estimate X0, Y0, and A0. We're attempting to find where the nuclear source is. So to avoid ambiguity, we need to say that we know the sign of Y0, or else we need to move in one direction and resolve the sign by then moving the sensing vehicle in another direction to decide whether Y is getting bigger or Y is getting smaller. But if you just move in a single straight line, there's a symmetry on each side of that line which you can't resolve. So here it is again, the source is at X0, Y0, the detector's moving along the X-axis. The source is radiating particles, they form an inhomogeneous Poisson process. There's a mean arrival rate, the value of which is dependent on the source position and the source strength. And there's measured arrival times, and we have to estimate the unknown information. So the natural way to first attempt an estimation is to form a likelihood function. And here's the likelihood function. And we have to find the X0, Y0, and A0, which are maximizing this. Now, maximization and minimization are really the same thing. It just depends whether you're standing up or in the southern hemisphere and upside down, right? So we're worried now about maximization, not minimization. So people worked on this problem, and they looked at the critical points of the likelihood function, and they obtained those by setting the derivative of the likelihood function with respect to A0, X0, and Y0 equal to 0. So you get three scalar equations for the three scalar unknowns. And then you might think, oh, well, I'll check and see if the likelihood function is convex. And so you write down the likelihood function at a particular place in X0, A0, Y0 space. And here it is. And you ask the question, is it convex? Because if it is convex, you know there'll be a unique maximum, and we can find the maximum. I guess it should be concave because we're looking for a maximum, but you can find it, and because of the concavity. Now it's not nice. It's actually not. This is the Hessian is not concave everywhere, or not positive left or negative left everywhere, unfortunately. So we cannot appeal to what we normally, or what we used to appealing to, or what we're comfortable to appealing to, namely the notion that the loss function is a convex or a concave. So the Hessian is not negative definite everywhere. But at any point satisfying the critical point equations, the Hessian is negative definite, and that's pretty easy to see. You see, there's the Hessian down the bottom, and then there's these constraints from the three equations, equalities above. And if you use those constraints in the Hessian, you find that the equation, the Hessian is negative definite. So every critical point is a maximum. And if every critical point is a maximum, Morse theory then tells you there's a unique critical point. So we found that just by looking at the behavior of the Hessian at the extreme points, not by looking at the behavior of the Hessian everywhere. You can find it by a gradient algorithm. And this is a sort of heat map of the likelihood function. And you'll remember you're using random data that's coming as a result of this random process, the Poisson process. So you can run many, many trials. And when you run many, many trials, I think it's far too hard to get an arrow on here. I can't get an error on here. When you run many trials, you'll get a different answer each time, but all those answers are clustered around the red point, I think it is, in the bottom right-hand diagram. The blue dots in the bottom right-hand diagram are where you end up when you estimate a position using different runs. And always these are random points, but they're clustered around the true value. Okay, so a very different example now on sample data controller design. So here's a picture of a controller using a sample data controller. The plant is continuous time. There's a discrete time controller preceded by an anti-aliasing filter and a sample in the whole element. So this is a kind of standard arrangement. And the controllers are described by a discrete time transfer function. And so we might have a minimal state variable realization defined by matrices A, B, C, D for the controller. And here's another minimal realization. Choose any matrix capital T and you can manufacture an infinity of other minimal realizations this way. So where's the problem? Now, when you're realizing a discrete time controller, you do need to do something like use finite word length representation of coefficients, or do some truncation when you do multiplication. You cannot work with totally real numbers. And as a result, different realizations give you different amounts of error, the error arising due to truncations or finite word length or something like that. And so some realizations in the kind of real world will be better than others. And signal processing people doing digital signal processing have realized this for a very long time and understood that you don't just want a transfer function, you need to know how to realize it to minimize these problems associated with finite word length and truncations and all this sort of stuff. So any actual realization is an approximation of what is desired, and so we need to ask, what's a nice realization? And that depends on the choice of this matrix T. And you can ask, what is the optimal realization? How do I find it? And what is it? So having described the problem, it's reasonable to say, well, is this really a problem, or am I just sort of splitting hairs and trying to get a 1% improvement? Here's an example. I've got two ABCD quadruples realizing the controller transfer function K of C. And without having told you how I found it, I've given you the parameters of the optimum one and the parameters of the one I've started with. And I've got truncation, which allows 1 decimal point. And if you look at this lower right diagram, you'll see that there's a huge difference between the closed loop performance you get with the optimum one and the closed loop performance you get with the non-optimal one. And the optimal one is almost on top of the ideal frequency response that you get with infinite word length and no problems. And the non-optimal one is way, way different. So the purpose of that slide is just to illustrate this is a genuine problem. So how do you go about finding the optimum? So in a sample data system, what you've actually got is a time varying system, and it's periodic and it's linear. So there's a closed loop operator that's a periodic time varying linear operator that gets you from the input to the output. And you could take any one entry of the system matrices realizing the controller and consider the sensitivity of this closed loop operator to the variations in that entry. And there's decades and books on how to compute such quantities, and it's really messy. I'm certainly not going to show you what they are, but you can compute such quantities. And if you put the squares of all of them together, that gives you an index of sensitivity of the input-output performance to variations in the parameters inside the controller. And you can then study how that index depends on coordinate basis change, replacing A, B, C, D by T inverse AT, T inverse B, CT. And you'll find that the performance index is unchanged if T is replaced by TQ for any orthogonal matrix Q. And so really what's important is T, but T times T transpose, which suppresses this having to worry about Q. And after several pages of calculation, this is a performance index that you get. JB and JC are computable quantities. P is a matrix whose square root will determine the coordinate basis change to get from your existing controller to the optimum one. The things under the integral sign are all computable entities. And JB is a bit like what's under the integral sign with derivatives with respect to B, and JC is a bit like what's under the integral sign except derivatives with respect to C. So everything for computing J is known, except you don't know what P is. And what you want is the P that minimizes J. And there's no analytic solution to that problem. And P is an n by n non-negative definite matrix. So the optimization task is to minimize that complicated function of P using the manifold of actually positive definite matrices. And one of the questions, of course, is there a global optimum, or is there only one critical point, and is it the global minimum? So you can obtain critical point equations, and you could obtain Hessian equations here. And you'll find again that J at every critical point has a positive definite Hessian. So that means, because at every critical point you've got a positive definite Hessian, that means there's a single minimum, and you can find it with the steepest descent algorithm. It's appealing to this idea again that comes from Morse theory that says if every critical point is a minimum and you're working in Rn, and effectively that's what's going on here, then with every critical point of minimum, there's a single critical point, and it's the global minimum. So you can find the optimizing the quantity by steepest descent, and then you can obtain T. So that's quite an old idea. So what I've been saying in these two examples, in the previous one dealing with the nuclear source localization, and this dealing with determining the fixed way finite word length controller realization optimum problem, which is pretty complicated. What I've been saying is you can use Morse theory. There's no differential equations here or anything, to establish that at any critical point of the index, you've got a minimum, and therefore there's a unique minimum, which you can find confidently with gradient descent. So now I want to start the next two examples introducing some differential equations. And the first is concerned with a thing called sphere world done by a roboticist called Koticek. I was not involved in this work. And it was done quite some time ago, about 30 years ago. It involves the notion of a potential function and a steepest descent control law that's supposed to drive you towards some objective. So you can imagine a particle moving in Rm, generally n will be 2 or 3, maybe occasionally 1, I suppose, under the influence of a potential field. And the way you represent that typically is as x dot equals minus grad v of x, where v is the potential energy. So it's a scalar function of position. And so we get a differential equation which says how the particle's moving. And you ask the question, where's the particle going to end up? So the particle has to end up where v has a 0 derivative, or f of x has a 0. Of course, it might be a minimum, it might be a saddle point. We don't know in advance. But the connection with Morse theory is quite a simple one. Equilibrium points of the differential equation are the same as critical points of v of x. The critical points of v of x are where its derivative is 0. And so these are equilibrium points of the differential equation. So we can formulate a thing called a navigation problem. And given the region where the robot moves, specify a v of x, which will guarantee that the robot moves to some prescribed point x0. So there's a few questions you should think about when you write down that problem. What's the region in which the robot's moving? Is it R2 or R3 or something more complicated? Or is it R2 and R3, perhaps with obstacles, because obstacles are clearly going to complicate it too. And do you want the robot to go to x0 always, or do you just, and if so, do you want to avoid any other equilibria, or do you just want to ensure there's a single stable equilibrium, and any other equilibrium is a saddle point, and so with a bit of noise, if you got there, you wouldn't stay there, you'd fall away and head further downwards towards, hopefully in the end anyway, the minimum of the global. So lots of people have found examples in the robot literature showing when you introduce obstacles, the robot can hang up at an incorrect point. That's well understood. And the issue is, one of the issues for them is, were they just not imaginative enough when they were trying to find a control law? Or do you hang up, or might you hang up at some difficult point, no matter how clever you were in generating the navigation function, which purportedly should take you to x0. And the tool to answer these sorts of questions is Morse theory. So let's think about R2, which is really what Koticek did. If a robot's moving in R2 and there's no obstacles, and the object is to navigate to x0, you just choose v as this, and x dot is minus gradient of v, and so you go in a straight line from where you start off to the desired endpoint x0. Notice that v is smooth and it's got a unique isolated minimum. The Hessian's non-zero at the minimum, and it goes to infinity when x goes to plus or minus infinity. So v is a Morse function. And this is the trajectory, as you know. It's the steepest descent in the trajectory, and it converges exponentially fast. And the same idea works for R3. So where it gets interesting is when we start to stick in obstacles. And so we can define a kind of space called sphere world. And sphere world takes some of Rn and sticks some obstacles in it in this way. First of all, we have a large sphere that bounds the whole workspace. And that's W, and that's closed. But then within W, we stick some obstacles, and those are those red dots, are there again spheres. And I've used less than or equal to signs or less than sign so that the workspace, which is everything in the big sphere apart from the obstacles, the workspace is closed. So I should say the free space is closed. The robot operates in the free space. The jargon is the workspace is the whole thing, but the workspace has got some obstacles in, and apart from the obstacles, you've got the free space. And then there's a little technical detail, which is you don't want the obstacles overlapping or projecting through the boundaries of the workspace and stuff like that. So you clear that. And also you don't really need obstacles which are strictly spherical. You can distort them a little bit. So Kotichek worked with a sphere world, and inside into the navigation problems provided using the Euler characteristic of the sphere world. And then, so I'm going to divert and just talk about the Euler characteristic of the sphere world and then relate it back using the Morse equations to the navigation problem. So you can get out your dictionary of Euler characteristics, and you can find Euler characteristics for a closed disk, an open disk, and a sphere. So the closed disk, it's always 1 in n dimensions, and the open disk, it's -1 to the n in n dimensions. And the sphere is what I've written here. And the open disk union the sphere equals the closed disk, or in 2 dimensions, an open disk and a circle equals a closed disk, and the same idea in 3 dimensions. And when you've got a set which is the union of 2 and they're not intersecting sets, there's a theorem that says the Euler characteristics add. So the closed disk, which is the first one, 1, and the open disk -1 to the n, and the sphere 1 + -1 to the n -1, obey this rule about so that the sum of the last 2 will equal the first one, just like the union of the 2 sets for the last 2 equals the set for the first one. So this rule about the union of sets and the relation of the Euler characteristic allows you to relate the Euler characteristics of W, which is a single closed disk, and so we know that that's 1. And the OJ, any one of those is a single open disk, and so we know its Euler characteristic. And W is the union of F and all these OJs. And so out of that, and this rule about adding Euler characteristics, you get this funny expression for the Euler characteristic of the free space where the robot's running around. So the robot's running around in a space whose Euler characteristic is 1 + -1 to -1 to the n. And it's that which, as I'll now argue on this slide, explains why it's not a matter of being sufficiently clever to solve the navigation problem with obstacles. It is unsolvable because it's the Euler characteristic of the free space prevents you ever being able to get a continuous control that will solve the navigation problem for all initial conditions. There will always be problems of the thing hanging up somewhere. So let's suppose that we got it. Someone said, well, I've got a potential function that works. This is the fundamental Morse equality that always holds. And if there was a unique attracting equilibrium point, so you could always get to x0 from wherever you were, you'd have M0 equals 1, and you couldn't have M1 or M2 or anything non-zero. This equation could not hold once M is greater than 0. If M0 is 1 and capital M is greater than 1 or more of M1, M2, M3, and so on has to be non-zero, which means there are cells or maxima or something like that somewhere in the space. And if you have all of M1, M2 up to M0, then in some cases you'll have a whole bunch of there'll be a single value of M0, but one other than 1, which might work. Okay, so that's a sphere world. And then with formation control, again, we're going to get a funny sort of Euler characteristic. So the idea in formation shape control is this. We've got a bunch of point agents, and we specify a set of distances between pairs of the agents, so that once we've specified this list of distances, the formation shape is specified. So if I had 3 agents and I specified 3 distances, say the distances between pairs of the agents, then the shape of a triangle would be specified. I'm not specifying in that process where the centroid is, or I'm not saying anything about its orientation, but I am specifying the shape of the triangle. And formation shape control is concerned with moving agents so that they will take up a shape which is specified using distances, like the 3 sides of a triangle. So we'll say that at time t, the actual formation shape's defined by some distances, dij of t, and we want a control law to get it to a set of prescribed distances, d star ij. So it's a formation shape control law. And the laws that people have been using have all been in gradient descent form. And the behavior of the laws for lots of formations are well understood. So let me give you some examples. If you've got a triangular formation and you don't start it off with the correct distances, but you use one of these laws, you will normally converge to a correctly dimensioned triangle, unless the formation is collinear. Or if you've got a formation with 4 agents and these 6 distances are all prescribed, and use one of these laws, you'll normally converge to the correct distance, except you may encounter some saddle points along the way, but with a bit of noise, you'll get through the saddle point and fall towards the correct formation shape. And really any rigid formation, not defining rigidity, but you can imagine what it is, it can be locally controlled. So a little aspect about these things is that there's always 2 formations at least that satisfy the distance constraints, because you can take a formation and make its reflection and you don't change any of the distances. But when you do the reflection, you get a second formation which you can't move to from the first while preserving all the distances. If I wanted to move from the top right formation to the top left formation, I would have to either come out of the plane and do this, or I'd have to let the distances move away from the correct ones and somehow reassemble. So there's always 2 formations satisfying the distance constraints. So this is all a little bit strange. Here's an example of what happens with a triangle. Let's suppose 3 distances are specified and they really are roughly determining an equilateral triangle. This is this, I haven't moved this. I think the zoom is interfering again.
Yeah.
Oh, there you go. I think we got one. So that's the controller. The controller's in action and it's turning that initial formation into an isosceles triangle, at least maybe equilateral. Yeah, how do we get this one? So if we aim to get the same triangle, but happen to start with the agents in a straight line, we never get to the triangle. The agents just keep going in a straight line. Roughly speaking, the middle one doesn't know whether it should go right or go left. And there's two possibilities that might lead you to the triangle. So this is a situation that's a bit like robot, except it's a lot more complicated. There are funny things that can go on that can block you getting to the desired end result. Here's an example of a typical control law. It is a gradient descent law. This particular gradient descent law is trying to minimize this error measure. The errors compare the squared current distance with the squared desired distance, take the difference and square it. So the Morse inequalities and equalities tell you here that it's not a matter of needing to be cleverer to ensure that no matter where you start from, you'll end up with the correct formation. The Morse equalities will tell you that it is impossible to cover all cases, that there's or they're telling you that there's always going to be some initial conditions where you'll run into a problem. And I'm just going to show you, this is the space in which we're working is the one down the bottom of this slide. And it's a cross product of the positive real line and a complex projective space in it, n-2, which sounds very, very complicated. And it sounds like this should be something going on in the pure mathematics department and got no place in an engineering seminar. But this is actually one way of talking about the space in which these formation control problems are evolving. And they're formation control problems where people have been striving or trying to come to grips with the fact that a number of the algorithms wouldn't work in certain situations. So to understand why they won't work, and in fact can never be worked by mind a simple patching, you need this sort of argument. And here are the equations that you get from the Morse theory, and for a triangle, here are the equations that you get from Morse theory using that particular Euler index. M0 is the number of minima, M1 is the number of saddle points with one unstable mode, M3 the number of unstable, the number of completely unstable or maximum. Sorry. Yeah. So if you look at those first three inequalities, and remembering that these M0s, M1 and so on, they're just non-negative integers, it's easily seen that you can't, there's certain combinations you can't have. And if you say, I'm going to have M0 equals 1 or M0 equals 2, that is, there's two possibilities for this stable formation, then those inequalities force you to have a non-zero M1 or M2, meaning there are necessarily other equilibria, saddle point equilibria, where the algorithm may hang up and it could only be rescued by noise. So this is analogous to robots, which in sphere world with genuine objects can never get a continuous law from every initial point that will get the robot to final destination. So there will always be some unwanted equilibrium points. So I'm going to finish by just mentioning some conclusions. So what's Morse theory? It's a tool for finding relations linking the number of critical points of different indices involving n variables. And sometimes it will tell you that there's a unique minimum that you can find with gradient descent, even in a non-convex situation. The requirement to always have convexity is illusory, because you need convexity at the critical points. And Morse theory has been used in diverse system theory problems. One of the references I gave you at the start is a book with a number of examples. And there is a generalization of the ideas which I haven't talked about. But to just say what it is, it's called Morse-Smale theory. And it lets you deal with x dot equals g of x, where g is not a gradient descent function. And it's a massive generalization of Morse theory, and that's the one that the power systems people are really getting behind to analyze their complicated collections of equilibria and to classify them, find out how many there are, and so on. So I think that's a good point to stop, and very happy to take some questions.
Any budget? It's code check, know that it was impossible to get smooth.
I think Kodacek was the first person to prove. I think he proved it, that you can't get a smooth
Control on.
Yes, that's right. I mean, he was using all these topological ideas, you understand.
Oh, okay.
Not me. That's not my interpretation of his work. That is his work.
That is. No, what about distant, non-smooth or even discontinuous control on?
Well, there is not a good, of course you can do a lot more if you allow yourself. There is not a good theory that say as Morse theory chapter 2 or, you know, Morse Coreless theory or something that tells you how to do it. And so that could be a big area for investigation, quite seriously.
The weird thing is the reason the descent algorithm works is because basically the functions are Lyapunov function.
For the descent algorithm, V of X is the
function.
Yes, that's right. That's right.
Any other?
Yeah, I have a question related to the definition of the Morse function.
Could you speak a bit louder?
Yeah, so I have a rather trivial question related to the definition of the Morse function. The first condition is that it seems the function should be like really unbounded. So how can we interpret it if we consider the function on like compact manifolds that are R-.
So when I introduced Morse function in the very early slide, it was a Morse function on the real line. Okay. So when you define Morse functions on a compact manifold, they just need to be bound. And in fact, if you were to go to a modern textbook, they'll kind of try to dispense with Rn or any infinite manifold on about page 2. And say from now on, we're just going to consider a bound manifold. But from an engineering point of view, you know, you need to be comfortable with the sphere and orthogonal matrices, or you need to be comfortable with R2 and R3, unbounded stuff. And that's where typically the Morse function has to have some kind of known behavior when X goes to infinity. Now, I could have made it so that it's negative in both directions. So this is just a point of view. There's no serious.
Thank you.
Oh, any other question from online? We have 30.
I had one quick question, Brian. Thanks so much. That's excellent talk. One interesting thing about convex functions is, if you add two convex functions, you still get a convex function. So with Morse functions, that the uniqueness of the minimizer seems like it probably won't hold, right? If I have two Morse functions that have unique minimizers, add them together, is the resulting function guaranteed to have unique minimizer, or is there anything that could be said about the number of minima?
So first of all, a Morse function doesn't have to have a unique minimum.
Mhm.
A Morse function is a function that has certain properties in order that the Morse inequalities and Morse equality can be written down for the function, okay? So now you're saying if you've got two Morse functions and those Morse equalities and inequality tell you in respect of each function that there is a single minimum, you're asking if you add them together, is there a single minimum? And the answer is what you'd expect. The answer is no. You just add together two parabolic functions or something, and you'll typically get two minima and a maxima, but a local maximum between them. Yeah. Does that answer the question?
Yeah, I was wondering if there's other relationships that could say, hey, the number of minima could increase by at most one, right? From each of the individual functions if you add two together, so forth.
Look, I think that's a very reasonable question. I'm unaware of whether it's been considered, and I'll add, I think the way to formulate such conjectures is to look at very simple cases where f of x is mapping from R1 to, or always mapping to R, but so look on the real line in the first instance, and then maybe on a circle, and see what happens there.
Right. Yeah, thanks.
You're welcome.
Any other questions from the audience? Yes.
So I thank you for the documents, it was very good. So I think I understand talking about critical points using Morse functions, but another part of your title was talking about stability without Lyapunov. And I'm not sure if I fully drew the connection to how we can talk about use Morse functions to talk about how stable those critical points are.
So you're right that I didn't make the connection clear, and it would have been clear if I talked about Morse smale, which I left out. So if you know that V of x is a Morse function with the property that there is for every critical point a minimum, you know there's a unique minimum, and then you can conclude that x dot equals minus grad V of x is necessarily going to converge to that minimum, or you can conclude that V of x is a Lyapunov function. So I suppose what I've been saying is that taking a Morse function view of certain V's may lead you to conclude that V is a Morse function without ever checking V dot. Okay, if there's a unique minimum due to the fact that every critical point is a minimum, you never need to look at V dot. It's right in there. Does that make it a bit clearer?
Yes, that makes it a bit clearer. So you just it's not necessary because you just know you can get there.
That's right. That's right. And you're moving from local behavior to global behavior. And just to understand that takes a little bit of a mental leap, I think. It is strange to me that you can say, I know the behavior here, I know the behavior here, I know the behavior, therefore it'll be this.
Very interesting. Thank you.
Any other questions? So Brian, it seems like, at least from what I hear, wonderful topic, and there's 2 points that I'm going to add. One is about the finite workers, because that's a problem that we have worked on for
interpretation is correct. Before, when we have to do optimization, we always ask questions, do you get the global minimum, right?
Yes.
And if you don't, and people will say, hey, people always lay this trap on, you know, and say, how do you know it's global minimum? You don't answer directly, they come out. It seems like you resolve the question to some extent to translate, we're not going to show convexity, but, right, if you can show this is a Morse function, I can do a countable test.
Yes.
To show a local minimum is actually a global minimum, because if you satisfy these conditions. But the challenge in that is you make this the problem complexity in solving the Hessian,
Yes.
right, rather than trying to prove complexity, because you have to do the Hessian to solve to solve the countable problem.
Yes. Look, I think everything you said was entirely correct and insightful. So you do the Hessian. I'll just add one thing to your remark about what people did in the signal process. This thing involving finding the nucleus, okay? There were papers around about finding the nucleus source. And they all said, we don't know whether you can always find it this way, but our algorithms seem to do a pretty good job. And it was known it wasn't convex actually. So people felt very uneasy about it. And then you come along and you show, you know, the more stereo is that you're in business, but just by looking at the recruiting points, if someone rescues everything. And maybe that's true for some of the signal processing stuff. I remember the old signal processing stuff just on an open loop discrete time, nothing sitting in a closed controller to the one. There were peak proof and balanced realizations, and things that sort of scale down to were often, and you could prove it directly. But with this standard data analytic to get